We said that for synchronous detector, the locally generated carrier must be well synchronized. Here we will see how the carrier acquisition can take place in DSB-SC system with the help of Costa's receiver. This is a special type of receiver designed to detect DSB-SC signal. Here we are assuming xt is the message signal. So xt cos omega ct is the DSB-SC signal. So we have received this DSB-SC signal. This DSB-SC signal is divided into two parts. We have two product modulators. One voltage controlled oscillator is used to generate this locally generated carrier. Voltage controlled oscillator means the output frequency of this oscillator is dependent on the input voltage. That means if input voltage increases from a certain value, some nominal value, then the local oscillator frequency will increase from its nominal value. Similarly, if the input voltage of the VCO decreases from a nominal value, then VCO output frequency will also decrease from its nominal value. That means output frequency is dependent on the input voltage. This is what we call the voltage controlled oscillator. The upper product modulator is directly multiplying this cos omega ct, cosine the original signal generated by this VCO with the incoming DSB-SC. But for the lower product modulator, the VCO output is first phase shifted by 90 degree to produce sine wave. So if this one is cos wave, after 90 degree phase shift, we have a sine wave. And this product modulator will multiply this sinusoidal carrier with the DSB-SC signal. So if we multiply these two, then we will get what we have seen in our previous discussion of phase error. After the low pass filter, we will have half of xt cos phi. Similarly, the lower channel output will be half of xt sin phi. This lower channel is called the Q channel or quadrature phase channel, and the upper channel is called the I channel or in phase channel. So in the upper part, the output of low pass filter is multiplied by cos phi, and in Q channel the output of the low pass filter will be multiplied by the original message signal will be multiplied by sin phi. Now try to understand the basic operation of Costa's loop. Assume that the local oscillator signal, that is the VCO output, is synchronized with the transmitted carrier signal, and for the time being phi equal to 0. So we are assuming first phi equal to 0. This phi is equal to 0. The output of the I channel is the desired modulating signal, because phi equal to 0 means cos phi equal to 1. So demodulated output, here we have the demodulated output, will be proportional to xt. But under this situation, since phi is equal to 0, phi equal to 0, that we have assumed, there is no phase error. So sin phi is also equal to 0. Since sin phi equal to 0, the Q channel will give you 0. So this section will be 0 right now. We can also call it as quadrature null effect, because sin phi and cos phi they are in phase quadrature. So because of this quadrature null effect, the Q channel output is 0, or rather the Q channel is 0. So this is the condition when it is locked and we are getting the output. Now assume that the local oscillator frequency drift slightly. This frequency is drifted slightly. That is, phi is very small, non-zero quantity. I channel output will be almost unchanged. If you can remember a property of this cosine function, so cos phi will almost equal to 1 when phi is very small. So the variation of cos phi will be negligibly small. So output will be almost equal to half xt. But when phi is small, sin phi is almost equal to phi. That means it is proportional to phi. Sin phi is proportional to phi when phi equal to 0. Phi equal to very small quantity. That means the Q channel output is no longer 0. Rather, some signal would appear at its output and is proportional to sin phi. So in previous case it was 0, this one, but now with a finite value of phi, it is not 0, it will have some finite value. Thus the output of this Q channel is proportional to phi, and it would have a polarity same as the I channel for one direction of phase shift in local oscillator, whereas the polarity would be opposite to I channel for the other direction of phase shift. Now this phase discriminator provides a DC control signal which may be used to correct local oscillator phase error. The local oscillator is a voltage control oscillator, as I said. Its frequency may be adjusted by an error controlled DC signal. That means whenever there is some signal present in the Q channel, the phase discriminator will identify that change in phase, and accordingly it changes the output voltage, so that input to the VCO will change and it will change the frequency. So this is the basic operation of this Costa receiver. Unfortunately, this receiver stops phase control in absence of any modulation. That means if we, instead of xt cos omega ct, if we provide this cos omega ct only, this one will not work properly. So in absence of any modulation, it will not work. So this is what you call the Costa's loop receiver and carrier acquisition in DSB-SC system. Now we are going to discuss quadrature amplitude modulation, QAM, which is also called quadrature carrier multiplexing. The bandwidth requirement of DSB-SC signal is same as that of standard AM. That is twice FM Hz. If FM is the bandwidth of the modulating signal, then the bandwidth of DSB-SC is twice FM Hz, just like AM. This bandwidth can be efficiently utilized to transmit two independent message signals by slightly modifying the conventional DSB-SC scheme. This bandwidth conservation scheme enables two DSB-SC modulated waves to occupy the same transmission bandwidth, and yet it allows for separation of two message signals at the receiver output. This is what we call the quadrature amplitude modulation. But this quadrature amplitude modulation is different from the QAM present in digital communication. You will learn digital QAM during digital communication class. But this quadrature amplitude modulation is in analog domain. So let us try to understand the transmitter and receiver sections. So first of all, assume we have two signals, M1T and M2T. First we need to modulate M1T using a balanced modulator that should produce DSB-SC signal. One oscillator must be there that will produce the carrier signal. The second signal should be passed through identical type of balanced modulator, but the other signal, that is the carrier signal, must be passed through a 90-degree phase shift to produce sine omega c t. That means for the first balanced modulator, carrier is cos omega c t. So here we have M1T cos omega c t. For the second balanced modulator, the input signal is M2T and the carrier is, instead of cos omega c t, the carrier is now sin omega c t. So here we have M2T sin omega c t. These two signals are added to form the multiplexed signal. So this is the transmitter for this QAM. Multiplex signal can be written as ST. ST is the multiplex signal. Now come to the demodulator part. At the demodulator side, we will receive ST. Mind that ST contains both M1 cos omega ct and M2 cos sin omega ct. It is containing both the terms. So we are receiving this ST. So what we do, we at the demodulator side, we use balanced modulator or product modulator that will multiply two signals. One oscillator will be there, synchronous oscillator, that will produce cos omega ct. So incoming DSB-SC here it will be multiplied by cos omega ct, and we must have another channel 90-degree phase shifter is used to change the phase of the carrier, and we have another balance modulator. Here the first signal, it was originally ST is equal to M1t cos omega ct plus M2t sin omega ct. So at the receiver here, in the balance modulator is multiplying this cos omega ct with this ST. So this output is 1t, it will be multiplied by cos omega ct. So M1t into cos square omega ct plus M2t sin omega ct into cos omega ct. After that we have a low pass filter with a cutoff frequency of FM Hz, where FM is the maximum frequency component of M1. So this S1t can be written as cos square omega ct, means half of 1 plus cos 2 omega ct. So M1 by 2 plus M1 by 2 cos 2 omega ct plus M2t sin omega ct multiplied by cos omega ct, that is sin of 2 omega ct. As you can see, it consists of three terms. This term is with the frequency of twice Fc. This term is also with the frequency of twice Fc. So these two terms will be eliminated by this low pass filter. This low pass filter will eliminate this term and this term. So only existing term will be S dash t is the output. So S dash t will be equal to M1 by 2. So at the upper channel we will get the first signal. So what happened to the second channel? So this signal is S2t. Okay. Then this S2t can be written as S2t is the multiplication of ST and sin omega ct. So we have M1t cos omega ct sin omega ct. This one is multiplied by sin omega ct. So plus M2t sin square omega ct. that is equal to m1t by 2 sin omega t cos omega t omega ct, that means sine of twice omega ct, and this one m2t means sine square omega ct means 1 minus cos square omega ct. That is equal to m1t by 2 sine 2 omega ct plus m2t minus m2t multiplied by cos square omega ct, that means half of 1 plus cos 2 omega ct. This one. So that is equal to m1t by 2 sine of twice omega ct plus m2t minus m2t by 2 minus m2t by 2 cos omega ct twice omega ct. That is equal to I am taking this as a first term, so m2t minus m2t by 2, that means m2t by 2 plus m1t by 2 sine of twice omega ct minus m2t by 2 cos twice omega ct. S2t should be passed through a low pass filter whose cutoff is FM2 Hz, where FM2 is the highest frequency component of the signal M2. This M2 is assumed to have a highest frequency component of FM2. So cutoff frequency for this low pass filter should be FM2 Hz. So once this signal is passed through the low pass filter, the low pass filter will eliminate this term because its frequency is twice Fc. It will eliminate this term as well because it is also of frequency twice Fc, and the output of the second low pass filter is double dash T. So the total circuit becomes this. This is the total circuit. S double dash T is the output of the second detector. So S double dash T can be written as, this one is removed, this one is removed, so only existing term is half of MT. So S double dash T is proportional, M2T. So S double dash T is proportional to M2T. That means at this port we will get M2T, and at this port we will get M1T. So both the channels, both the baseband signals can be recovered and they are isolated from each other at the receiver. So this is what we call the quadrature carrier multiplexing. Now, for satisfying operation of the coherent detector, it is necessary to maintain coherent phase and frequency relationship between the oscillators used in the transmitter and the receiver parts of the system. This type of multiplexing system, quadrature amplitude system, finds its application in color television. So this is all about QAM in analog domain.